connecting to the cloud server, and it should be recording. All right. So let's begin with the review. Hopefully my thing works. And I actually had to borrow the cable from the library because I forgot. I'm just gonna say modeling. Oops, that's ugly. Move my setup modeling methods. All right, so modeling methods review. Let me see if I can zoom in a little. That should be better. All right, modeling methods review. So what I'm gonna do is, for the sake of time and for the sake of simplicity, I'm gonna kind of like tell you guys what kind of things you guys need to know to prepare for the exam. I'm gonna probably not gonna dive into examples, like actual numerical examples for the sake of time, but if we have time, I can always go back and show you the type of questions that you can expect. Or as I go, I can show you the type of questions. So one of the things that you have to know, very, very important for you to know, are what are the main, and I should probably speed this up when I upload it. What are the main sources of errors? So can someone tell me what are the main sources of errors for all numerical calculations? Yes, so you have two sources of error. One of them, you said it was round off. And I'm not looking at the Zoom right now, so I apologize. Round off and what else?
Truncation.
So I'm gonna mute them. So truncation. So you have runoff error and you have truncation. Very, very important that you know that those two are the main sources of errors. And also very important that you know how, like where they actually come from. Like runoff error comes from the finite accuracy of computers when we're storing real numbers, and truncation comes from taking something like the Taylor expansion, the Taylor series expansion, and truncating it so that we can create a relation about like some information of how we derive the finite difference. So they both come from completely different places, but they're both sources of errors. You have to know how to store, how to convert, I'm sorry. So if I say something like convert real, where real is the keyword, convert real numbers to binary. And when I mean this, I mean try, God, I'm still getting used to this screen. Try something, I'll say try something like x equals to like 0.24 or something like that. Try something that has a decimal. Try something that is a real number, because these are better indication of that you actually understand how to go from binary to decimal. If you're lazy, you can always, there's no prohibition of using the calculator. So if you're using something like a TI 36X Pro, a Casio FX 1115 ES or something like that, those can actually do this. TI-84, TI-89, they can do binary conversion back and forth. If you're doing something like a TI-30X, kill yourself. No, if you have something like a TI-30X, that one, I have no idea what it can do. It's a very basic calculator. If you have one of those like kitchen calculators that my grandma used to have, yeah, that might not help you. So make sure that if you have a calculator, it actually has some usefulness to it, because you can use a calculator. So the more the calculator can do, the better you can just move on. So if, and this is more of like a star, I will say, connected to this one, I will say, God, I'm having such a difficult time with this screen. So storing, I will say like storing a real value produces what error? So what error produces what error? If I store a real value, there again, these are the two main the main sources of error. So again, if you want to store a real value, you're going to introduce some round of error to the computer because of the finite accuracy of the computer memory, because you cannot store decimals. When you take a decimal value, something like 0.24, and you convert it to binary, it's infinite. It goes on forever. And you will see that when you start doing examples of decimal to binary conversion. they go on forever. So the computer has to round it. The computer has to store it with the memory that is available, and that introduces the run of error. So something else that is very important is how do we express zero? Um, I will say in single and double precision. So this is for real. This is not for integers. How do we express zero in single and double? And at this point, I wish I knew how to use the actual ruler in here. So excuse my very beautiful lines that I'm about to draw. This is actually supposed to be like chopped right at the middle. So how do I move this? I want to get rid of the people from Zoom. I'm sorry. I'm gonna cut it right in the middle. And I'm gonna do the same exact thing. Can I like lasso this and go? Where's your professor gonna do that shit, huh? Fucking copy paste on the fly. Okay, there you go. Here, here. So if you can like remember this table, that will be like the best thing that can happen to you. Not a table, but like this picture. So this one over here, this is gonna be single, as in you're single because nobody loves you, and this one is gonna be double, as in double precision. So single precision and double precision, these are both for real values. And the way that we can express the values for here is we go from -10 to the 38 to -10 to the -38. You have +10 to the -38 and +10 to the 38. And then for double precision, you have -10 to the, no, this is actually positive 308, -10 to the -308, and then 10 to the -308, and then 10 to the 308. So what happens is, if you want to represent zero, zero is right here. Jesus, that's so fucking huge. This one. If you want to represent zero here in the middle, okay, whatever. If you want to represent zero here in the middle, you have to approximate it because, again, the finite accuracy of computers, zero cannot be stored exactly into the computer memory. So we have to approximate it. And the way that you will represent zero as exact as possible, theoretically speaking, will be on single precision. You can either use -10 to the -38 or 10 to the -38. That's pretty freaking small. Or in double precision, you can use -10 to the -308 or 10 to the -308. So any of these two in single precision, any of these two in double precision. Sometimes they might tell you like, oh, what is the smallest negative value that you can express in single precision? That will be this one. What will be the negative, the largest negative value that you can express in single precision will be this one. The largest negative value in double precision will be this one. The smallest negative in single will be this one. The smallest negative in double will be this one. And the same thing with the positives. So it's better if you kind of like write this table down or this graph down and remember it have it handy during the exam, because looking at this, then you can see like, okay, if they're asking me how do you express zero in single precision, it will be either this guy or this guy. If it's double precision, this guy or this guy, whichever you see on the multiple choice question. By the way, the exam is multiple choice question, but it can also be multiple answers. So, and I know they're trying to see if we want to like move into actually looking at the work. So do as much work as you can on the paper, because we actually go through those things. So if something doesn't match what you picked because you were in a rush or something like that, you're gonna get some questions. Um,
Excuse me, Rodrigo. I had a question.
yes.
Can you use these tables to also say what the largest number can be? So 10 to the 308 would be the largest number.
Yes, so this will be
Okay.
the largest positive number in double precision. This will be the largest positive number in single precision.
Okay. Thank you.
So the positive and the negative, that's kind of like the keyword. Because if I say negative largest, I mean this too.
Right. Okay. Makes sense.
So
Thanks.
definitely keep that in mind. Also, what I mentioned before, the errors, very important, because when we do, as I mentioned it before, I say when using, and I'm kind of like going back at this point, I say when using Taylor expansion, and I'm just gonna use an arrow. I'm gonna say what error. So what error do we introduce? Just kind of like repeating myself, what error do we introduce if we do a Taylor expansion to do the finite difference approximation? Truncation, exactly. So we do truncation because we are halting truncation. We're halting an infinite process. And we, by doing that, we are, it's not as pure anymore, because if mathematician says infinity and we don't take it as infinity, that is not, it's not worthy again. You have to know how to perform finite difference. So I'm gonna put it here as a start, because this is as something that you're actually gonna do by hand. So learn, I'm gonna say learn finite difference and finite difference. And what I mean is approximation. So approximation has 2p, right? Okay, so, and then this one is again, forward finite difference, backward finite difference, and central finite difference. And if you want to know how to do those, they're on your formula sheet. What you can expect to have is something like this. Like they can give it to you two ways. They can either go something like this, where they have, let's say I do like a little table here where this is x, as this is the function evaluated at x, and they give you 0, 1, 2, and then this is like 2, 4, 6, and they say, hey, I want you to calculate the f prime at like x equals 1, for example, using forward finite difference. So you know that will be like f at that point, at that x, plus delta minus f of x divided by delta. And what that's going to be is, this is, the x is right here. So the x is 1. So there's 1. If I go from 1 to here, like if I do from here to here, I'm adding 1. If I go from 1 to 2, I'm adding 1. So delta is equal to 1. The step on the x-axis is equal to 1. So this is x. X is equal to 1 plus delta. That will be when x is equal to 2. So this right here, this is f of 2. This, once you plug in the values. So f of 2, the value is going to be 6. So minus f of x, again, x is 1. So this is actually f of 1. So f of 1 is 4. So 6 minus 4. And at delta, I said that it was 1. So in reality, this is 6 minus 4, which is 2. Right? So that's how you find a difference. Depends on the formula. You have forward, you have backward, you have central. They can also, instead of giving it to you like this, they can give it to you in a very easy way. They can say delta plus x is equal to 2, delta minus x is equal to like 1, and delta is equal to like whatever, 2, like the time step or something like that. And I'm sorry, and the x. They're not going to give you the delta. They will give you like the x. So they can give it to you in two formats. They can give you the table, or they can give you the actual things to plug in into your function. You just have to use the function. That's all you have to do. Another thing that is very important is to know what machine epsilon is. What is machine epsilon? So what is machine epsilon or machine precision? They're the same thing. What is machine epsilon? You don't have to know the actual value, but you have to know what the definition is. And I'm not going to write it down, but machine epsilon, as far as the exam goes and as far as theory, is the smallest number, the smallest value that you can add or subtract from 1. And the computer is still able to tell a difference. It tells you that something happened. So that is the definition of machine epsilon. Something that I saw that it was kind of new, not new, but like, you know, this is something that you saw this semester, is what happens. I showed you the range before, the range of the values for real values. Like what is the largest, what is the smallest, how do you represent 0? But what happens, I'm going to say what happens if underflow or overflow. For what happens if you have an underflow, if you pick a number that is smaller than the range that you're allowed to have, or what happens if you pick a value that exceeds the largest value that you're allowed to input into the system. So again, the best way to study for this question will be to go back to the quiz questions that you saw in class, that it had either a critical or non-critical error, what type of error it was. That's very important for you to know. Very, very important. This after this point, we kind of like get more into the actual Newton-Raphson and secant method and the root seeking. So all of this from here up, going up, all of this has been more of like how what you guys saw at the beginning of the class, all of the different things about computer, all of the information about finite difference approximation and binary and how the computer stores things. After this point, we actually get into the root seeking method. So I'm going to draw this like this, and I'm going to say, now we're going to start talking about the root seeking methods. Before I move on, does anybody have any question? Okay, perfect. So root seeking methods. We have what is known as the fixed point iteration. So we have fixed point iteration is actually one of the methods among all the other methods that we saw. So this is called the fixed point iteration. And what you do, this is actually in your formula sheet. What you do is you take the equation that you have and you rewrite it in a different form. You kind of like solve for the variable that is your x, in a sense, becomes your function. You take a function that is something like, let's say y equals 2x plus 1, and what you do is you solve for x. You move everything to the other side, and that in a sense becomes your function because you're solving for that value and based on the value of the other one. So I don't remember exactly right now how you exactly do it, like how you see it in the class, but that is the idea. And why is this thing not letting me erase that? Get out of here. Okay. So fixed point iteration and know how to write. I say and know the possible form. And what I mean by this, what I mean by the possible form is, again, if I give you a function, can you write it in fixed point mode? If the fixed point form, which is, again, you solve for the independent variable. You move everything to the other side, and that becomes what is known as the fixed point form. Go back to the notes, see what they do when they have the equation and they say we're going to do fixed point iteration, like the square root algorithm or whatever, where you move everything to the other side and you solve for the independent variable. That is what is called the fixed point form. So they're going to give you a function and you have to put it in the fixed point form. Very important. Something that is very important is how can you tell if a guess is an initial guess? So that is part of this. How do we know? How do we know if x sub 0 is good? And even more important is it converging? So this is something that is very important to know if an initial guess is a good initial guess and if the actual process, like if we're going to eventually converge rather than go through the process and then hope for the best. There is an equation at the end of your formula sheet for exam 1. If you look at that equation, there is an actual mathematical thing that says g of, I think it's like g of x evaluated on a certain x has to be less than 1. I believe it's something like that. Or is the g prime of x? That is something that you have to check. I believe is the g prime of x evaluated at whatever iteration, whatever value of the root that you find, it has to be less than 1 in magnitude for it to guarantee convergence. So go to the last page of your formula sheet, look at that, make sure you understand that a statement is given in a little of mathematical lingo. So make sure that you understand and make sure that you understand how it applies, because that is how you check if an initial guess is good or if your code has the chance of convergence. If you're doing fixed point iteration, if you actually have the chance of converging rather than going through the whole process. Because when we do numerical methods, we don't always just go, okay, whatever, I'm gonna try x sub 0 is equal 20 and pray to God and hope for the best. Like we actually have ways for us to test if something is actually gonna converge. If they were to tell you like, okay, if they said, if instead we want to try, Newton-Raphson, and I'm just gonna say Newton, I guess I'll spell the whole thing. Then if they say, okay, if instead of doing that, if instead of doing fixed point iteration, we want to try Newton-Raphson, then you will go back to the function. You will go back to the function that you were provided, and you will put it in the Newton-Raphson form, which again, the Newton-Raphson form is the next approximation of the root. It's equal to the current approximation of the root minus the function evaluated at the current approximation of the root divided by the f prime of the current approximation of the root. So if they ask you to put it in the Newton-Raphson mode, in the Newton-Raphson form, that will be the equation that you will use. If they ask you to put it in the secant method form, you will use the equation for the secant method, which you're provided all of these equations, all of these formulas, you're provided them in the, what is it called, in the formula sheet. Okay, so in the same manner, can you guarantee convergence? The same test that I told you before that I said, how do we know if the initial guess is good? How do we know if something is convergence? You can use that exact same. The last, it's literally at the last page of your formula sheet. There is a mathematical like definition. You can apply that to everything. You can apply it to Newton-Raphson. You can apply it to fixed point iteration. And the idea is that you apply it at every single x. Every time you do an iteration, you obtain a new x. You can do the test with that x to check if you're actually indeed convergent or if you're not. So that will be a kind of question that you will see. Like, can you also, I'm going to write it here. I say, check for convergence. Yes, it's something like G, I think it's like G prime of X, where X is like the current X, has to be like less than 1 or something for all the values of X. So this means for all values. That underscore like upside down A means for all values of X. So that's the test that you use. Again, at this point, usually your exam will be, your 3 exams will have this form. You will have you will have 25 questions in total. 25 questions in total. 15 of those questions are going to be like a mix between conceptual questions and short answers. Like you can just calculate them real quick, get the answer, move on. The last 2 big problems, we usually pick 2 topics. So in this case, we're going to pick most likely Newton-Raphson and bisection, and we'll give you 5 questions of each. So the last 10 questions of the exam are going to be like, for example, like Newton-Raphson. I will give you the equation, I will give you an initial guess, and I will say, okay, starting from here, I want you to do Newton-Raphson, and I want you to find the next approximation of the residual. I'm sorry, of the root. So you will do the calculation, you will find x of 1. Okay, can you now find the residual at the new iteration? You find the residual. Can you find the iterative convergence? You find it. And then I say, okay, can you find the residual after 3 iterations? So you have to do the iteration 3 times and then use that value to do the calculate the residual at the 3rd iteration. Same idea with bisection. Again, the equations for residual and iterative convergence, and I will write them in a second, they apply for everything. Bisection, secant method, and Newton-Raphson. If you look at your formula sheet, the equations to find the residual and the iterative convergence, they're all the same. But I'm going to talk about that in a second. I do want to mention something else, and it's very, very important. Make sure you know, and this has to do with today. Make sure you know the speed of convergence. Oops, helps if I can write. Convergence. By the way, sorry for the cursive handwriting. It's the only way I know how to write. Make sure you know how the speed of convergence. So this means, again, linear, super linear, kind of like being super friends. Oops. Super linear, which is another way to say friend zone. Super linear and quadratic. So you have your linear, you have your superlinear, you have quadratic. One of them belongs to Newton-Raphson, the other one belongs to bisection, the other one for secant method. So make sure you know all the speed of convergence. And now I'm going to talk about Newton-Raphson and bisection. So I have about 15 minutes. So let's draw another line here. And I feel like this one is going to be, let's try this. Oops. So that is as far. Let's do like a quick recap. So we talk about the root seeking methods. Make sure you know how to do fixed point iteration. You don't actually have to like perform fixed point iteration. You have to know how to put it in the form of fixed point iteration. If I give you an equation, do you know how to put it in the fixed point iteration, in the fixed point form? How do we know if the initial guess, if I give you an initial guess, is there a way for you to test if it's a good initial guess? And also, can you check for all consecutive x's if it's going to converge? If I have a good chance at converging, refer to the last page on your formula sheet for the equation for that. If instead I ask you to use Newton-Raphson or I ask you to use any other type of method, you have to be able to go back to that function and write it in terms of Newton-Raphson. Because they will ask you, they will give you a function and they will say like, what is the form of Newton-Raphson? And then you have to know the function, you have to calculate the f prime and then kind of like put it in this form. That's all you have to do. Because again, it's all kind of like steps. It's all steps. If you know how to do Newton-Raphson from beginning to end, you're gonna be able to answer all of these questions. And in the same manner, we can check for convergence by using, I don't know exactly if this is the formula that is on the last page. I think it is. Okay, perfect. Right. So my brain is not fried yet. All the I was gonna say excessive drinking, but I don't drink. All the nights of no sleep, I still have some neurons left. Make sure you know how the speed of convergence. So make sure bisection converges linearly, Newton-Raphson converges quadratically, and secant method converges superlinearly. However, these things slightly change when you have a double root. Like Newton-Raphson, when there is a double root, I think it converges linearly. So do go back to your notes, go through those things because there are specific cases in which they may converge slower or they may converge faster. If I remember correctly, I think when there is a double root, Newton-Raphson doesn't converge quadratically, it converges linearly. Again, going back from the beginning, what are the main sources of error? Runoff and truncation. That's at least what we're concerned with in this class. Know how to convert from real numbers to binary. Try something like 0.24, 0.29, something 0.32. And you can always check with the calculator. Learn how to do it with the calculator if you don't want to learn how to do it by hand. But again, we're going to be going through the actual like paper. So you have to show work. Don't just say, I plug it in the calculator and I got this number by magic. Starting in a real value produces, storing a real value produces what error? If I take a real value, 0.32, if I want to store that in the computer has to turn into binary. Binary will be infinite. You will find that out once you start doing binary by hand. And how does the computer go about storing that? It has to round it. It introduces round-off error. How to express zero in single or double precision? Right here, you can memorize this this sort of like graph, or you can write it down, put it in like a flashcard or something, keep it at hand. This is how you do it in single precision and double precision. Again, this is for real values. This has nothing to do with integers. This is all real values. When using the Taylor expansion, what error did we introduce? Taylor expansion is an infinite process. If we want to use an infinite process with a computer, we have to chop it somewhere. It cannot be infinite because the computer doesn't understand infinite. So we introduce a truncation error. It's not necessarily a computer error, it's a man-made error because we are assuming, we're doing the best thing an engineer does, assume things and hope it's not wrong. Nobody dies, you're good. Someone dies, you're not good. So learn finite different approximation. All the formulas I provided to you in the formula sheet. Do make sure to go through the formula sheet. Your formula sheet is your best friend. Do not rely a lot on it because it's going to bite you in the ass on exam 2. The formula sheet for exam 1 is very helpful because the material is very straightforward. Formula sheet for exam 2 is not as helpful. So do not try to just kind of like, wing it and get a misconception of the exam, because then you're going to do like shit on exam 2. But know how to do forward finite difference, backward finite difference, and central finite difference. I will say try to learn about the whole error proportionality, because something like this, something like if you have, I do not like red, let me go back to black. If I have something like this, I'm going to do the forward finite difference. If I have this minus f of x divided by delta x, something that you're going to see on your formula sheet is there is something that is the big O notation. I have delta x right here. This is the error. If you have O and then d of x, this means that they're proportional. O is the error. It's the error of the produced by the higher order terms. All those errors that we're ignoring. And this is proportional. So this is something that you saw on a quiz. So it's very important that you go back and take a look at it. For forward finite difference and for backward finite difference, the error is proportional to the time step. or I'm sorry, to the step size, to delta x. So if I were to take delta x and reduce it by half, if I were to reduce delta x by half, my error will be reduced by half. It's different for central finite difference because in central finite difference, I'm going to say here central finite difference, the error is actually proportional to delta x squared. So if I were to reduce my delta x by half, I actually reduce my error by 1/4 because 1/2 squared, it's 1/4. So yeah, CDF, central, oh, I'm sorry. I don't know why I wrote CDF. Central finite difference. There you go. I wrote it in the middle. But yeah, if I were to say, okay, if I reduce my delta x by half, for example, if I'm gonna do half of whatever delta x I have, what's gonna happen to the O is gonna be 1/4 of the error. So there is a higher magnitude because of the delta x. So very important that you remember that. And again, just know how to do it by hand. Just know how to use the function, the equations. We're gonna give you either a table or we will give you the values, and it's literally plug and chug. It's literally plug, use it, and an engineer's favorite friend, not having to know the theory. What is machine epsilon? Again, not the actual value because it changes from machine to machine. It's more of the what does it represent? The smallest number that you can add or subtract from one and still be able to tell the difference. That's literally the answer. And what happens if we underflow or overflow? I don't remember exactly, but I do encourage you to go back to the quiz and take a look at your of your notes because it changes depending on who you ask. Computer science people might have a different perspective on it than people that are more traditional engineer oriented. And we already went through this thing. So now I have about like 7 minutes. So Newton-Raphson, and let me do this real quick. Newton-Raphson. If I'm doing something like Newton-Raphson, and you can expect the same for bisection. Let's say I am given, so I will be given my function f of x and my initial guess, x sub 0. You could also, I'm going to say may be given the f prime. You may be given the actual exact evaluation of the derivative. Don't cash on it. Like don't account for that. If you have to go back and learn a little bit about chain rule and how to do like actual calc 1 derivation, highly encourage you. Don't just bank on the fact that you're going to be given it's not going to be an easy equation. You're going to have some trick in it. So definitely know, like have a table or something. You're not going to get something crazy like some cotangent square, some crazy shit like that. But you may have a sine, you may have a cosine, you may have a tangent. Who knows? But just to be on the safe side, remember how to do that. So you will be given the function, you will be given the delta at the x sub 0, the initial guess. You may or may not be given the f prime, and then you can start the process. And you can say, okay, if I want to find, I'm going to write the equation right here one more time, x plus 1 equals x sub n minus the function evaluated at that x sub n divided by the f prime of that x sub n. And here are the other functions. The residual at whatever iteration, it's going to be the absolute value of your function evaluated at that particular root. And the iterative convergence at the next one, it's going to be the root at the new iteration minus the root at the previous iteration. The reason I do it like this is because if you put a 0, there is no iterative convergence at the initial guess because you have nothing to compare it to. So different residual, they can ask you for initial residual, like x sub 0, but they will never ask you for epsilon sub o, because what are you going to do? X 0 minus x minus 1? Like you cannot do that. So be very careful with that. But what kind of questions can you expect? Those are the formulas that you will use. And then they can ask me something like this. They can say, okay, so at the iteration 0, that means before I even do anything, they may ask, may be asked, you may be asked for initial residual. And there's a high chance that you'll be asked this. So maybe ask for initial residual. And what this means is that you will be asked for R sub 0, which will literally be take the absolute value of your function evaluated at the initial guess. So if the initial guess is 2 and you know your function, plug that bitch into the function, absolute value of the result, that is your initial guess. And then now that's the only thing that you will be asked at the 0th iteration at the initial guess, because again, there is no epsilon sub 0. So let's say first iteration. So I'm gonna find my first iteration, and sometimes they say first, sometimes they say I equals 1, like in the project. So on my first iteration, I'm gonna say, okay, x, if I put a 0 for the end, I'm gonna have the new iteration, it's gonna be equal to my previous iteration minus the function evaluated at that previous iteration, in this case, my initial guess, divided by the prime evaluated at that initial guess, right? So this will give me that x of 1. This will give me the new approximation of the root. And I know all of this. I know my initial guess. I know how to plug. I hope to God you know how to do this. You know how to plug the value into the function and evaluate the function. And if you have the prime, or if you calculate the prime, you take that x sub 0 and you plug it into the f prime. Now, you have to do also, and you will be asked, or you may be asked, to calculate the residual at the first iteration, which again, absolute value of the function evaluated at the value that you just found, this value right here, this guy, you take it and plug it in here. I'm going to delete that line in a second, but you take that and plug it in the f in the evaluation of the function. So that's how you calculate the initial residual. And in the same manner, you can calculate the epsilon. You can calculate the iterative convergence at the first iteration, and that will be, as I mentioned before, the new root, the one that I just found, x minus 1 minus x sub 0, not x minus 1, x sub 0 minus x sub 1 minus x sub 0. Sorry, it's like my brain is like over here, my mouth's over here. But yeah, you take the absolute value of the difference. That tells you the magnitude, how far is one x from the other. And this is the same exact process. You keep doing this exact same thing. Let's say I have to do 2 iterations for whatever reason. I hate myself, or the exam is asking me to go up to 3 iterations. Okay, then I say the second one, the second approximation of the root is going to be equal to the first approximation of the root minus the function evaluated at that first approximation divided by the f prime at that approximation. And you might be asking, Rodrigo, you're so full of shit. We don't know what x1 is, but actually I will say, bitch, hold up, we do. I feel like I'm selling something. You take that x sub 1 and you plug it right in here because you found that value. So that's why all of this iterative method, that's why we use computers, because it's literally do this, calculate this value, now take that value, use it on the next step. Now take that value, use it on the next step. You cannot make a human do this because they're gonna fuck it up. If you have to do this 20 times, you are gonna screw it up at some point. That's why computers are so good, because computers are dumb in the sense that they understand arithmetic, but this is perfect for them. Repetitive work, they don't make mistakes. Unlike me, I fuck it up like 5 times if I'm doing this by hand. But yeah, that will calculate the x sub 0. And then in the same manner, I can take that r sub 2 and again, just the evaluation of the function at the second one. And the epsilon at the second one will be x sub 2 minus x sub 1. And this is the same idea. However many iterations we ask you, the residual at whatever iteration, for all of them, you have to calculate the iteration. You do not have to calculate the residual for all of them. You do not have to calculate the iterative convergence for all of them. It's up to whatever. So it's a good idea. What I usually recommend the students, if you feel prepared for the exam and you want to make the most out of your time, go to the last problems and start with those first. The last 10 questions, because those are these problems. Newton-Raphson and bisection. Those are gonna take you a lot of time. You don't wanna waste a lot of time with the first couple of questions that you can like kind of like just guess or type of thing, because then you're gonna run out of time. Like, and I know in exam 2, a lot of people get so hung up on some of the initial questions, and then they get to the last questions where you have to do Gauss-Seidel or like really complicated stuff, and they're like, what the fuck am I doing? So because you're running out of time. So time is the biggest constraint. As far as this class goes, time is the biggest constraint. Time is the #1 complaint that I hear for many, many students. The math is not hard. That's what they all say. The math is not hard. Calculations are not hard. It's the time. And that's why it's very important that you're very organized. That if you, whatever you're working on your sheet of paper, don't be flipping that freaking thing like 20 times and writing all the borders or something. Um, Try to be organized. Try to have all your values so you can go back to them. Because if I ask you, okay, what is epsilon at the second one? You have to go and look at this value, and you have to look at this value. Otherwise, you cannot calculate x sub 2. Epsilon sub 2. You cannot calculate the third convergence because you need the values for x sub 2 minus x sub 1. So you have to look on your paper. Okay, where is the root of x sub 2? Where is the root of x sub 1? But yeah, that's Newton-Raphson. Bisection, same exact idea. The difference with bisection, and I'm not going to work a whole example because I do want you to look online how to do bisection method. It's not complicated. It's very straightforward. What you do is you're going to be given, I should actually say that actually. You will be given, what time do we end this class anyhow? 15 or 20?
3:20.
Don't look at me. I got no clue. What? Oh, 20. Oh, wow. We still have time. Perfect. Listen, they only pay me to teach. They don't pay me to keep tabs on the time. So bisection method, you will be given the function and you will be given an initial bracket. So you will either be given like this. You will be given like a bracket that has number, comma, another number. So that's your A and B. Or they will define it like this. They will say A is equal to whatever number and B is equal to whatever number. So how do we go? Actually, let me check the Zoom chat. Okay, I see people saying thank you. I guess people are like being like bye-bye. So given the function of x and the actual bracket, we can start doing the actual bisection method. And the way that you do the bisection method is if you have, I guess I have enough time to do it like real quick. If you have something like this, and that's horrible. There you go. If you have a function like this and you want to evaluate it at 2 points, let's say this is B and let's say this is A right here. So if I evaluate A based on the graph, just visually, just look at the graph. If I evaluate f of B, is it going to be positive or is it going to be negative? This is the x-axis. If I evaluate f of B, is it going to be positive or negative? It's going to be positive, right? If I evaluate at the point A, is it going to be positive or negative? It's going to be negative. So that means that if I take f of A and I multiply by f of B, am I going to get a positive or a negative? I am going to get a negative. What this tells me is that at some point, my curve crossed that x-axis because my function changed sign. So there is a root somewhere in there. If they were to have the same sign, then no, there is no root because there wasn't a change of sign. The way that I will go about this is I will say, okay, let's say I want to do my first approximation of the root, x of 1. What I'm going to do is I'm going to take that A plus B, so this one, and I'm going to divide them by 2. Whatever this value is, that will be the new approximation of the root. This is my first iteration. That is my new approximation of the root. And let's say it falls right here. It falls right at this point. I'm going to call it x of 1. So x of 1 is right here, right? I calculate that thing. And because this is my first approximation of the root, very important, just like before, you can calculate r sub 1 and epsilon sub 1. Sorry if I'm not like working the whole problem, but this builds on the previous stuff we saw. It's the same exact functions. So I have x sub 1. And what I can do is I can take that x sub 1 and I'm going to evaluate that that function at x sub 1. What sign do you think it's going to have? Just visually, just look at it visually. It's going to be positive. When you actually calculate it by hand, you will have a positive or a negative. But the f sub 1 is positive. So what happens now is this was my iteration number 1. What happens now is I'm going to look at the left and I'm going to look at the right. So at A, I know that it's negative. At the new root, it's positive. So there was a change of sign. So my root is on the left side. My x sub 1 and my b have the same sign. So I know that there is no root in there. So I can say, okay, fuck this side. I don't need that side anymore because I know that there's not a root on that side. So now what I do is I say, okay, my new A, and you can either write it or you can just say whatever you want. My new A is going to be equal to A because I'm keeping the left end the same. And my new B is going to be equal to what? Yeah, it's gonna be equal to x of 1. So because now I'm using this area. And then I do the same exact process. So now we're back to this, we're to the second iteration. X of 2 is gonna be equal to A plus, not B, x of 1 divided by 2. And again, you can calculate the receipt, whatever based on that result, you can calculate the second residual and the residual at the second iteration and the iterative convergence at the second iteration. And you do the exact same thing. The whole idea is every single time you're taking, you have your like your ends. And what you do is you cut it right in the middle and you say, okay, is the root on this side or is the root on this side? And if you know it's on the left, you say to the right, okay, fuck off, I don't need you anymore. Then you focus on the right. I'm sorry, on the left. And then you do the same thing. You reduce every single time. You're like reducing, reducing, reducing. And the idea is that if the root is right here, at some point you will keep like shrinking these margins up to the point where you're like right at the root. Like your A and your B are gonna have the same exact value, and then you can conclude that that is the root. This is one of the best methods. It's just very slow, but you can throw that thing at everything. If you have a tangent that is doing some weird shit, if you throw Newton-Raphson, it's gonna have a stroke. If you throw some bisection method, you know where tangent is discontinuous, so you pick your bracket accordingly. But yeah, this is what you can expect for the exam. Do you have any questions? Do people in the Zoom have any questions? It's better if you use your microphone.
This was
No?
really helpful.
Okay, perfect. All right, I'm gonna stop the recording. And hopefully this one we actually get it. Do you want to stop recording? You will receive an email. Looks like